Hello, audible?
Yes,
Yes, please. Okay, great. Today we take your basic like AC/DC circuits, huh? Circuits, okay? Fundamentals. So as you know, there is a electrical circuit components or elements. So there is a active passive element. Active means source like a current source, voltage source. Passive component, if we discuss with passive component, you have a resistance, inductor means inductance, resistor, inductor, and capacitor. You know, it is like a conductor. Huh? This has a length in meter. This cross section area A. So this resistance, when there is a flow of current, okay, when current is flow through this conductor, it opposes, there is some property of conductor is oppose the flow of current. That is known as a resistance, okay. So this resistance of conductor is directly proportional to length and inversely proportional to cross-section area of conductor. Therefore, we can write R equals to rho L by A. Here rho is the resistivity. What is it? Resistivity. Resistivity means it is ohm meter unit, or it is also called as a specific resistance. Correct? Inverse of resistance, resistivity is called conductivity. Its unit, symbol is sigma. What is the unit of conductivity? It is known as a Siemens. Okay. Now inductor is actually nothing, but it is a coil, solenoid coil. What is the solenoid coil? We have a soft iron core, and an enameled copper wire is wound over this. Okay, it form a coil, solenoid coil. Okay, correct. This is the coil. Here, the length of coil. Okay, there also this cross section of coil. Like if we represent a coil like this, like this. So this length of coil, and this cross section area of coil. Okay, area of coil, number of turns, n suppose here. Okay. When we apply like here positive or negative, there is a current is flow I. Then there is a current in this direction. Now flux will be right, and your flux exit from this end, and again it is enter to this. Okay, so this enter here, exit here. So that's why it is called south pole. This is north pole will form. Okay. Now suppose what is the total flux? Number of turns, it is multiple. Your flux is multiple through the coil. Okay. So like we consider as a per turn, like it is a phi. Then total flux is n5. This is the total flux. It is represented by psi. Yeah. Total flux link, linkage flux, linking, total flux linkage here. Now what is the inductance? Hello. Inductance of a coil is nothing but it is flux linkage per unit of current. Means total flux divided by current, that is n phi by I. Okay, this is called as a inductance of a coil. It is also property of a coil which oppose the change of current through it. Change of current. Okay, the unit is Henry or millihenry. Like here, the unit of resistance is ohm, kilo ohm, mega ohm, milliohm, less unit. Or bigger unit is kilo ohm maybe. Okay. Okay, dear, this is the inductance. You can now drive this formula complete. Now phi equals to MMF, magnetomotive force, divided by reluctance. Again, this reluctance is denoted by S. Okay, S equals to same like it is. It is again L by mu 0 mu R A. What is the mu 0 mu R? Relative permeability. or free space permeability. Okay, and MMF is nothing but it is ampere turns, Ni. Okay, coil Ni, that is the ampere turns. It is MMF is ampere turns. This is MMF. Now if we put here value phi equals to Ni, then into 1 by, if you do that, it's 1 by means divide by L by mu 0 mu r A. Then finally it becomes mu 0 mu r A Ni by L. This is the phi. Okay. Then now therefore, L equals to, now if we, it is n phi, this is phi, n square. Now become mu 0 mu r, okay, n square. Now I, it is I divided by I. First we write the phi, mu 0 mu r A I, this, divided by L into n by phi I, this I cancel, and this n become n square. Okay, here is only one n. Now we can write this L equals to mu 0 mu r n square A divided by length. So this is the inductance of solenoid coil, okay, of a coil. Here mu 0 mu r is the permeability of free space and iron core. N is the number of turns, A is cross section area, L is the length. Okay, dear. Any doubt here? Capacitance, it is the property of a, what is the this capacitor means? It is made of a two positive and negative plate. There is a dielectric medium. Means dielectric material we put like either sometime air insulator or mica, what is we use, oil type also capacitor. So suppose this is positive, here charge is accumulated, here negative charge accumulate when we give the supply. Positive plate, negative plate, it is polarized means. So this capacitance when we calculate in terms of electrical terms, C equals to total charge per unit voltage, okay, Q by V, C equals to, okay, it is coulomb per volt, that is called farad, okay, or microfarad we can make. Where it is coulomb per volt, it is like. Now, so suppose this distance between two plates is D, and here plate area, this plate is like this. For a parallel plate capacitor, this plate area is A, suppose, then very simple, capacitance is directly proportional to area of plate and inversely proportional to distance of D, or this C equals to epsilon 0 epsilon r A by D, farad or microfarad. Okay, this is your capacitance for parallel plate capacitors, correct? Okay, dear, so here we discuss the R. This is called capacitance, property of a capacitor, capacitance. This is called inductance. Inductance, like this has a resistance. Hello? Resistance. Okay, dear. First is resistance, second is inductance, and this is capacitance. This is noted by C, this is L, this is R. Okay? And now if we connect in AC or DC circuit, so now we discuss with one pure capacitor or resistor in AC. Pure resistor or inductor and capacitor in AC circuit. AC means sinusoidal. When we apply this pure resistor, inductor, capacitor are connected in. Suppose to have a pure resistance, symbol of resistance is this. This is inductance, we use a coil. For capacitor, we use a inductor, capacitor. Okay. Here, this is negative plate. Okay. This is L, this is C. This is the symbol of resistance, inductor, and capacitor. Okay. Here, when we apply here across this resistor, AC supply, same like here AC across this pure inductor or across this capacitor. So here AC means V equals to Vm sin omega t. Here this is V equals to again Vm sin omega t. AC sinusoidal. Okay. Then there is a, if you apply sinusoidal current voltage, then current is also sinusoidal. It's flow through this. Now, due to this current, the drop voltage across R is VR, VL, and there is VC. Okay. If we see the now when we represent with the vector diagram, vector or phasor diagram of voltage and current. So here we represent the in AC, what is the effective value? RMS value. So we represent RMS values. Okay. So suppose this is your, volt in resistance, your voltage across R, this drop, and this current, both are in same phase. There is no phase difference. Okay. Correct. So this is your voltage, this is your current. They have a phase difference is 0 degree and then cos phi. Therefore, power factor Cos pi is 1 unity. Okay. Here before this phasor diagram, actually we also calculate, you know the current. Now we calculate a current. Okay, voltage we know. This is your applied voltage. Okay, phasor. Now I equals to V by R. Now V is the Vm sin omega t by R. Then this part is the current voltage by resistance. It gives the peak value. Im sin omega t. Okay, so see this two equation 1 and 2. The current and voltage are same phase. There is no phase difference. But here if we calculate the current in inductor, according to Faraday's law, induced voltage is is directly proportional to rate of change of flux, or it is d by dt of n phi, n d phi by dt. Correct, na? E equals to means voltage induced, self-induced voltage, or VL. Okay, this is the voltage induced. Okay, according to Faraday's law, this is the equation. Then induced voltage, we can write this. Okay, or it is V equals to total over this. N is a constant, so we can write this way. N phi is the total leakage, not leakage, it is linking, flux linkage. Now by definition of inductor, L equals to psi by I, means N phi by I. Correct, na? As we have written initially. Then N phi, therefore N phi, total linkage, flux linkage, is Li. Okay, this. So if we put here d by dt Li, then it is okay this. So this is the equation for voltage. Correct. Then from this we can calculate current. Voltage equation we have here. If we calculate the current, it is from this, it is di by dt. And di by dt equals to V, or L is go this side, then it is divided by L. If we do integration both sides, then it is, integration with respect to t, that is it convert into I, and this is come. Now L is constant, that is it is outside V dt. Correct? Okay. With respect to this omega t, Okay, T. Now please, I equals to 1 by L integration. What is the V? Vm sin omega t and dt with respect to dt. Now here Vm is constant, it is Vm by L outside. Then sine is minus cos omega t. And here you put the omega t. Then with respect to dt, then omega is divided in integration. Now we can write this Vm by omega. Omega means it is called as a L. So what is the omega L? It is XL. It is the inductive reactance, okay? Tu reactance, okay? Omega L equals to 2 pi Fl, okay? Please remember. The unit is ohm. It is also oppose the flow of current in inductor, okay? This is like a resistance, okay? It is same behave like a resistance in the, this is a ohm resistance, like a resistive. Then this represents the current, okay? And this if we take a minus outside, then cos we can write na sine pi by 2 plus omega t. Sorry, minus omega t. So this is Im. If minus sign go this side, then it convert into sine omega t plus, and this become minus. It means 90. Pi by 2 means 90 degree, okay, in a degree. So this is your current equation. So see, observe the equation 1. Actually, now only you have to remember this is the current equation in inductor, okay? And this is your voltage waveform. If we compare this, there is a 90 degree lag na, in waveform. Okay, here in resistance, if you draw the waveform, okay? Suppose this represents your voltage waveform. In in a resistance, your current is in same phase, means when it attains zero and peak value at same instant of time. Here it is. At same, when the voltage is zero, current is zero. Magnitude may be different, peak value may be different, but it same instant of time it is zero. Okay, so this is the your this is your current waveform. Okay, I. So that there is a no phase difference. But if we see in inductor, suppose this is the voltage waveform. Then your current is 90 degree lag. It is 0. This is pi by 2. This is pi. This is 2 pi. Means your current is either start from here. So this is the pi by 2 phase difference, okay? And this is the lag. Okay? This 90 degrees lag, your current is lag in 90 degree, okay? Correct? In phasor diagram, you can see this is your voltage VL. Then current is lag in pure inductor by 90 degree I. Then here cos 90, you know, cos 90 if you calculate it is come 0, lagging. It is in ideal inductor, the power factor of ideal inductor is 0 lagging. If you see the power factor reading, power factor meter is like this. There is a scale of power factor meter. Okay, here it is 0, here is also 0. This is maximum unity 1, unity power factor. Now this side is lead, this side is lag, lagging. It is 0.9, 0.8, 0.7, 0.6, 0.5 like this, okay? Okay, like 0.8, 7, 0.6, 0.5 like that. It is 0 here. Same like here. Sorry, 7, 6 like this, okay? In ideal, your reading either here, it is unity here or either it is here. Generally, it is 0.8 lagging, in general case, okay, your power factor usually in inductive loads, AC circuit, okay. Because there is no, it is impossible your circuit as a pure inductor or pure capacitor, okay. Same like in case of capacitor. As I told, in capacitor C equals to Q by V. Then Q equals to CV. This is charge. And you know current equals to I equals to dQ by dt. Q. Then current equals to voltage is this. There is a derivative of Q means CV. Okay. Now C is comes outside. C is a constant, then d by dt of V. Or it is C d by dt of what? Vm sin omega t. Then it is CVM. If you derivate na sin omega t with respect to 2, it comes omega cos. Okay. Now this we can write omega CV M. Okay. And this we can write sin omega t. Sorry. Sin pi by 2 plus omega t. Now, my dear, this Vm by, we can write now 1 by omega c. This 1 by omega c equals to xc. Xc equals to 1 by omega c, please. That is in ohm. This is capacitive reactance. It is capacitive reactance, okay? Correct? And here, sin, this we can write omega t plus pi by 2. Plus na a plus b or b plus a equals to 0. Or we can write it is, because this is a unit is ohm, xc. It is Vm by xc we can write. This is a current. Okay. This is current. It means Im. this equals to I equals to Im sin omega t plus pi by 2. Okay, so if we compare these two equations with voltage, your voltage is Pm sin omega t. So this current is lead. Okay, and suppose this is your voltage waveform. This then in the capacitor, no, current is lead means when your voltage zero, current is like this. This lead, I. This is I. Okay. Okay. So this is L and C. When now this is impossible because inductor also have a resistance. When if there is an inductor coil, so it consists of wire. This is a practical coil. When we talk about the practical, not ideal, practical coil. So it has a if we draw the equivalent circuit of this coil, we draw like electromagnetic coil. This coil has an inductor and it also has a resistance. So we can represent by this. This is your equivalent circuit of a coil, okay? Practical coil. Correct? Okay, yes. Now, here we discuss there is a circuit. First is RL series circuit, means your R and L are in series, or second is R and C are in series. Sorry. Capacitor you have, okay? R and C, or when all the three in series, yeah? Here we discuss the three circuits, okay? Here in capacitor, if we see the vector diagram, this is your voltage, suppose, across the current is lead with 90 degree, okay? Here is zero leading power factor in practical capacitor. Here, this when we apply the voltage here as sinusoidal, current is flow. Due to this current, there is a drop across R L. And here is a total source voltage, RMS value, okay? Then now if we draw the vector sum, see this, because current is same in through this all elements, RMS value. So see, this is your current, suppose, okay? This is your current, okay? Then the voltage drop due to this current, it is in phase with current only. Correct? So this is VR. Now drop in, so it is a total, this is total voltage drop. Actually, this is I, but year to year, this is a VR, okay? Now, drop in inductive drop, it is perpendicular to this. So if we calculate, this will give you total voltage, V, source voltage. Now, total voltage and this total current, total current. This is your total current. This angle is give phi. So this is the power factor angle, okay? In this case, your cos phi is power factor. If it is less than 90, then it is a lagging power factor, okay? 0.8, 0.7, whatever it is. This is a vector sum. V equals to VR plus IVL. Now, this is IZ, total voltage, impedance of circuit. IR, IXL, drop. This is IR, this is IXL, drop in reactance. VL equals to IXL. IR equals to VR equals to IR. And V total V equals to IZ. Then II cancel, then Z equals to R. Either vector sum or we can write in imaginary, real and imaginary part. XL, okay, JX. This is your impedance. We can impedance triangle R. Inductive reactance is positive always. If we draw the quadrant, this is plus, this is negative, this is plus, this is real axis, positive, this is minus real axis. This is plus j omega, this is minus j omega, origin. So this capacitive reactance is negative actually. So please remember XL equals to omega, j omega L. Okay, and this is X equals to 1 by j omega actually. When we j omega c, if you solve that comes minus j by, sorry, minus j by omega c, okay, like this. It is always negative, okay. Means we can write it is, okay. J omega c, it is negative, okay, minus j terms here. Plus j omega minus, sorry. Is minus J omega C, or we can write J by 1 by J omega. Okay, minus omega C, negative. Here we talk about, J omega L, XC means, sorry, XL, R and XL, that will give you total impedance Z. This is the phi. Then cos pi R by Z ratio. And this is a right angle triangle, then Z we can calculate magnitude, R square plus XL whole square, okay? This is in ohm. Then in circuit current we can calculate the total applied voltage by total impedance. It is in ampere. Okay, so power factor, impedance, current. Okay, in ampere. Same like here in here if you apply the same like AC voltage, here is also VR, VC. In this also your suppose this is the current. Now drop in resistance, it is in phase with current. But this is your inductive drop, sorry, reactance, capacitive reactance drop, VC. Then this will be your total V. Then see total V and total current. This is your I, na? So this is phi. It is lagging negative angle. Same like your capacitor, impedance is VC. This is R. This is, as I told you, this is negative, XC. Then this will give you Z. This is phi. Okay. And now when this all three components are there, it is more interesting. Now generally depends, it is circuit is inductive or capacitive overall. R, VL, VC. Now suppose current is depend. Now it depends on the frequency. Okay, because XL and XC depends on flow. R is independent of frequency, it is a constant. But like XL equals to omega L, X equals to 1 by omega C. Omega means it is 2 pi FL. This is 1 by 2 pi FC. Ohm. Okay. As you know, this is direct. XL is directly proportional to frequency. Omega is also frequency. It is a frequency, okay, in radian per second. F is also frequency, but it is in cycle per second, okay? That is called hertz. It is direct proportional to frequency. This is inversely proportional. It is directly proportional to frequency. X is inversely proportional to frequency. Okay. So suppose here voltage V total and F is the frequency. This is V total. Suppose this is your current. Current will show with red. This is your current in the circuit. Okay. Let us this reference. Due to this current, drop in resistance is in phase with current. Now drop in inductance is positive, means upward. It is VL. Drop in capacitor, it is due to current. It is in downside. Minus, no, it is negative. VL, okay. So you know this effective value. Sometimes capacitive is more effective than it is, downside is more. But let us be well, this VL XL is greater than suppose when inductive reactance is greater than XC. In that case, this is now this opposite value here we subtract from this side. So net will come here. Net value. So up to here, this will give you VL minus VC, correct? This vector, this here to here. Okay. Then this VR plus this difference will give you total voltage, and this total voltage and current is angle, phase angle. Okay. If you calculate here total voltage, VR vector plus VL minus VC vector, okay, this sum will give, or it is IZ, IR, here VL this plus, no? IXL minus IXC. If we take a common, I is common outside, then it is R plus, XL minus XC we write, okay? This is impedance. Or if we calculate magnitude of Z, it is R plus R square plus XL minus XC whole square. Okay, dear? XL minus XC whole square, okay? Ohm, okay? Correct? If we talk about the impedance, here impedance triangle, my dear. So this is your resistance, okay, R. Now this is XL, okay, XL. This is XC here, downside, XC. The net reactance is in the circuit because they have opposite. So they cancel this part and this part is cancelled. The net reactance in the circuit is XL minus XC. Okay. This is your Z. Then this is phi. Okay, dear. Understand this thing. Now come to Now we talk about the resonance, very important. Maybe they ask resonance in AC circuit, okay? Now maybe AC circuit are series or parallel, okay? According to that, this resonance is considered as a resonance in series resonance and parallel resonance, okay? Here we discuss only series resonance. So when this all component, when it is a condition, what is the resonance? This is the condition in series RLC circuit. Okay, series RLC circuit. Suppose if this is a RMS value of voltage and frequency here, then current is flow through this circuit. So see, this resonance is nothing but it is the condition. Resonance is the condition. It is a condition in AC circuit when net reactance of circuit, reactance means X, okay, net reactance become 0, or inductive reactance equals to capacitive reactance. Either you can write XL equals to XC. This is the condition for resonance, okay? So to achieve this condition, either it is a evidently, maybe it is occurs naturally, or we create. Okay, how we create? So to make the equal value of XL or XC. So how we can, either you take a variable C, we vary the C in the circuit, then at a particular value that become equal, or we vary the frequency, we fix value of RLC, then we vary the frequency. Okay. So if suppose here I draw. Here we write the parameter like your R, XL, XC, resistance, inductor reactance, capacitor reactance, then R, XL, XC or Z, then current, power factor, cos phi also you can observe. With respect to, suppose this is your, here we take a frequency F or omega. Okay. As I told, this resistance has a fixed value. R is constant. But you know, XL, this inductive reactance is XL is directly proportional. So as your frequencies increase, XL is increased. Correct? Directly proportional to frequency. And inductive capacitive reactance is negative. You know? Hello? X equals to 1 by omega L. When omega means frequency is 0, then it is infinite. My dear, it is negative, negative. This is positive. So at infinite, it is 0. When omega is 0, it is infinite. So this is coming from infinite and always negative. When your frequency is infinite, then this omega c is 0. So at infinite, it touch this 0 line. This is your XC. Always it is in negative quadrant. Now we draw the net reactance XL minus XC. So it is coming like this. at some particular value, actually, yes. Okay. Now at a particular value, this difference is become 0. Means like this here. At this particular frequency, this is what is this value? This is capacitive reactance and this is inductive reactance. They are equal. The net reactance is 0. Then if further increase the frequency, now it is inductive. It become inductive. Correct, na? It is like that. So it is X. X means XL minus XC. So initially this is capacitive. Then at some particular frequency, it become a 0. This is your X. Okay. What is the frequency at this point? F naught, suppose, or omega naught. That is called resonance frequency, resonant, or frequency of resonant frequency. Okay. Now, if below this frequency, that is called lower frequency, lower. This is called upper frequency. Okay. Now you know. If we calculate now total impedance, so your total impedance is R square plus omega L means XL means omega L minus 1 by omega C whole square. So initially, due to this, your impedance is infinite, and when omega is when omega is 0, this Z is infinity. Omega is 0, Z is infinity. When omega is infinity, then Z is also infinity due to this. Okay, so Z is at 0, it is infinite. And at resonant frequency, when omega is not omega naught, Z equals to R. Why? Because net reactance is 0. This XL minus XC becomes 0. Okay, because they are equal both. It means your impedance of circuit. I will show you that. This is your impedance. It touch this 0 line and it is a Z impedance. So at resonant frequency, it is minimum. It is Z equals to R only. So at resonance, your circuit behave like a resistive circuit. And what is the power factor? It is unity. So now if we calculate the current, current at under resonance, it is V by Z. So if your Z at starting infinity, then current is 0. So your current will start from here. Okay, current will show. This is your current. So when your impedance is minimum, current is maximum. Again, the current is reduced to 0 when impedance is infinity. So this show you current. It is a peak value or I naught, maximum current at resonance condition. Okay, dear. It means at resonance, under resonance, Under resonance, first XL equals to XC or omega L equals to 1 by omega C, or this omega we take this side, then omega square equals to 1 by LC. Actually, this become at a particular frequency that is called omega naught. Omega naught. Then omega naught equals to under root 1 by under root LC. LC. So this is your radian per second, your frequency of resonant. Or if you 2 pi f naught we can write na, this omega equals to. Or you can write f naught equals to 1 by 2 pi under root LC. This is in hertz. Resonant frequency in hertz cycle per second. But your condition is L is in Henry. C is in farad. Okay, unit. Please. Hello. Correct, na? This is the resonant frequency. Now this at resonance, this second, if we calculate impedance, then Z equals to, as you know, R square plus XL minus XC whole square. So this is, they are equal, it means it is 0 part. Then Z equals to under root R square means R only. It is minimum. The impedance of circuit under resonance is minimum. Then you calculate a current. Current I equals to V by Z, or it is V by R only. So it is maximum current will flow under resonance. Then if you calculate a power factor, so if your impedance, if you draw your phasor diagram, phasor diagram, suppose this is the current. Okay, due to this current, drop in resistance is in phase with current, and these two drops are equal. This is equal and opposite. They cancel. So this VL and VC cancel each other. Then your voltage, total voltage equals to VR only. Okay. Actually R small रहता है इसमें. Okay. Current, suppose I. This is your resistive drop. They are cancel each other. Okay. This total voltage is VR only. But this voltage is not 0. This is there. VL naught, VC naught. The magnification of voltage across L and C. Actually, it is I naught XL. This is I naught XC. That is large value but opposite. They cancel to each other. Okay, dear. Equal and opposite. So this is the resonance condition, and sometime in ETO there is a question on resonance circuit. So आज के लिए इतना ही है. This is like one general concept. Tomorrow we solve some questions on this. Okay. Please. LHC or LC. Okay. Resonance. We discuss this question tomorrow, okay?
Okay, sir.